DLS, Work, Lynch, Stockmeyer. And remember, what partial synchrony says is that the world is asynchronous, but there is some point in time which you do not know when, and you do not know that it happened or not. But after this point in time, the system does become synchronous. And this is kind of the definition. And somebody asked me here, so even after this event happens, you do not know that it happens. Right? So it's not that you get a signal saying now we're after GST. Right? All you know is that there is some point in time after some finite number of steps that this will happen. Okay, so why do people care about this strange model that mixes synchrony and asynchrony? Well, this is because this has a huge real-world success in the benign case. So if you've looked at like large-scale distributed systems, things like Paxos, Zookeeper, Raft, it used to be that all the big internet companies use this. Google, Microsoft, Facebook, Yahoo. But now, even if you're a medium-sized or small-sized company, then you're using some sort of Zookeeper or some sort of fault-tolerant replication scheme. And so, yeah, this is kind of there's two definitions. So one is that there is a finite bound; it's just unknown. That's kind of one definition, and the other is this definition that says that it's unbounded, and after GST, it's bounded. So these two definitions, you can show that they're equivalent. Again, this is the DLS, right? Okay, so why do people like this model so much? Yes?
Could you elaborate what you mean by benign case here?
Benign means that not a Byzantine failure, but omission failures. So machines can crash. In particular, like, Google was worried that they have a lot of infrastructure, and if there's like one machine that knows where everything is, and this machine crashes, now they don't know where everything is. So they said, let's replicate this one machine to 3 machines. And so then you build something like Paxos, they actually built Paxos, right? And the reason is that this gives you fault tolerance, but it's not a Byzantine fault tolerance. It's fault tolerance against an adversary that can cause omission failures. So why do people avoid synchrony? Why did Google, which has a complete control over its network and so on, not decide to take like a fault-tolerant protocol that assumes synchrony, but says I want to build a fault-tolerant protocol that actually assumes partial synchrony? These guys are extremely smart, and they thought about this a lot. And I'm not going to explain all the rationale, but really, at a very high level, if you build a synchronous protocol, it forces you to decide what your timeout is in advance. You have to hard code this timeout delta into your protocol. And then if you hard code this thing, then you are kind of stuck between two bad choices. And so one choice is you put it too small of a timeout. That means that you're always being timed out, and that means that maybe you lose liveness or sometimes even safety. And if you put it too large of a timeout, then you cannot move very fast. You can't move at the speed of the network. You're kind of always waiting so something might happen. This is kind of similar to what we've seen in the Bitcoin model, where you have to set this hardness parameter. This is something similar in this trade-off. And the nice thing about these partial synchrony protocols is because they provide you safety in an asynchronous world, then they typically provide you with the ability to move at the speed of the network. So you can make progress without waiting a specific hard-coded bound. And that's appealing to many system builders. Okay, so really what we'd like to do is we'd like to build a partial synchrony protocol. So I didn't mention this, but so in the asynchronous world, we have lower bounds saying that you have to use a quadratic number of messages. And so that's kind of annoying, because we'd like to get a linear number of messages, because remember, our goal is to kind of imitate Bitcoin. Bitcoin's Nakamoto consensus, that's linear. So we tried with asynchrony, it doesn't work. There are lower bounds for n squared messages and n squared words. Yes?
So the systems that you mentioned, they have n squared messages?
Oh, no. So they're worse. But so they're both built on Cashin's work, on this work here, and they're doing like a very strong batching to get. I can talk a lot about these protocols, but yes, yeah, I believe people are working on a lot of other variations. This is going to be a big topic. But question is, can you get some notion that's maybe in the best case linear, and so optimistically linear would be interesting. Yeah, and so this is kind of the nice thing about asynchrony, is that it allows you to make progress without having a parameter. And so our goal here is to kind of get linear protocols. That's one thing. So we want to spend a linear amount of communication. The other thing is that we want to get chain quality. So we want to get some sort of notion of fairness. So the amount of blocks you get to put in is proportional to the amount of blocks you have, the amount of votes you have. And you also want to get responsiveness, and I'll define responsiveness a little bit later, but at a very high level, responsiveness is this notion that you move at the speed of the network. So you're not kind of waiting every time you kind of wait a time out of delta and then you do one more step, you wait a time of delta, but you can move as fast as the network. So if the network is actually very fast and things are very nice, then you can move very fast too. Okay, so here again I'm going to go with a little bit of history. So one of the most influential papers here is PBFT, Practical Byzantine Fault Tolerance by Castro and Niskov. Highly recommend to read it. This is from 1999. Really great protocol. And it's kind of inherently quadratic, so the number of messages is quadratic, and somewhat pessimistic, so it kind of always assumes the worst case. And people ask, so people try to say, well, we'll use PBFT in all these permissionless systems and so on, and there's a lot of effort to do that. And I guess one question is, can quadratic number of messages scale? And so yeah, if you have just 15 members, then that's fine. 15 squared is no problem. But if you have 2,000 members and you really like to have like a large-scale consensus protocol, then 2,000 squared is actually a big number. So you want to, again, go back to a linear communication. And so there's this kind of very nice work, Ziziva, which both uses optimism and reduces latency and also kind of gets a linear cost. So it improves PBFT by getting a linear communication cost. And this is a famous paper, SOSP 2007 Best Paper Award, and a prestigious journal 2 years later. And this is well known in our community, and it turns out to have like a serious safety violation. So this is kind of one lesson I've learned, that you get all these people that don't come from academia and make these strange claims, and you say, well, that doesn't make sense to me. But the fact that people in the academia make these claims doesn't make it 100% sure that it's correct. So my lesson here is, if you want to understand something, read it, understand it, and then figure out if it's correct or not. So I think I read this paper several times, and only when I tried to improve it did we actually figure out, like, you really, really try to understand what's happening there, and you realize that it's broken in kind of a fundamental way. And people miss this, right? This was kind of a celebrated. This is not a paper that was in some lousy workshop. This is SOSP best paper.
Fundamental is equivalent to fatal?
A safety violation.
The idea cannot be recovered by some...
Oh yeah, there are different protocols, sure. This protocol is completely, yeah. So this protocol is wrong.
Not about the implementation that they wrote.
No, it's not the implementation. Yeah, it's the protocol is wrong. Okay. Yes.
Was there a fix?
Yes. So there's a fix, and you can go online and look. This is some of our papers. The fix is if you understand this, then you do the correct view change. But the thing is that it was not a typo, or sometimes you have errors where people mistakenly replaced lines. This is kind of a bug in the algorithm level, not in the spec or implementation level. Anyway, it's just a nice kind of a personal. So we have kind of a follow-up work on Ziziva where we actually correct this mistake, right? So we use the Ziziva approach, but we kind of fix the view change to so it's we believe it's safe. We have a proof. Don't trust us. Yeah, and so the normal case is linear. So basically, if you have a leader, it's elected. Then now every time it wants to send a message, that costs linear number of messages. But if you want to replace a leader, then that's still a quadratic number of messages. Okay, so it's a kind of a middle way. And one of the problems is that if it's if you want to get chain quality, if you want to replace leaders all the time, then actually you're going to pay this quadratic cost all the time, because view change is kind of the hard part of the protocol. It's the part that replaces leader all the time. And so then kind of, to me, completely out of the blue, and somebody who is not part of the distributed computing community, I guess, published a master thesis with this Tendermint protocol. And he's claiming that he implements a variant of DLS. But it turns out that he basically takes PBFT and he finds a way to improve the view change to be linear. Again, these are all simple changes, but we all missed it as a community, or we didn't. He did. He found it. He was the first to find it. But again, this is kind of a nice place where somebody from the outside thinking hard about this problem, I guess, found kind of very nice new algorithmic ideas.
Can you hint sort of what's the general idea of going linear?
It's extremely simple.
If you have PBFT, if you have Byzantine, you have to worry that the general is Byzantine. So this should be done by checking among the soldiers, and this is n square. So how do you avoid the n square?
I don't have it. So I'll say the following. In PBFT, what you do is you have to send a vector. I'm saying something that basically only for Eli. You send a vector of values, and then you can check, you as a replica can check that the primary chose from this value the maximum value. Okay, so there's a vector, and you see the vector, and you see that the primary chose the maximum value. And in what Tendermint says is just send the maximum value, and if that maximum value is smaller than what you previously shown, ignore this leader. That's the trick. It's very simple. I mean, it's obvious. It was there, from 1999. People should have done that.
What was the S square lower bound? Where did it apply?
In the asynchronous model, and I'll talk about the synchronous lower bound too. This is the partial synchrony model. And this is also like linear. Again, this is linear in if you have a per leader and per view change. Okay, this is not for agreement. I'm still cheating about agreement, because agreement you might have f bad leaders. So you have to do f bad changes. That's where your quadratic bound is. Yeah, and so this is a nice thing. Their idea was that basically take PBFT, do a linear version of PBFT, and then also pay a linear cost for these view changes. Again, protocols are very simple. I teach this, and everybody understands it. It's, or maybe understand it. Let's see the exercises. But even they, so even they had like some sort of recent liveness bug in the pseudocode. This is less fundamental. This is like, they wrote the pseudocode and they kind of got the pseudocode wrong. This goes back to, even when you have a conceptually correct algorithm, when you write the pseudocode, you might again kind of make some sort of small mistakes. And it's not just the pseudocode; it's the code itself. And so they updated the white paper and they updated the GitHub to kind of fix these things. So I guess my point is, going back, there's a lot of challenges in kind of verifying these protocols are correct, from the conceptual level to the spec level to the code itself. And I guess one of the things that these two protocols don't have is, and PBFT did have, is that whenever you do a view change, you actually have to weight delta. So unlike PBFT, in PBFT you pay a quadratic number of rounds, a quadratic number of messages when you do a view change. Here you're doing a view change which is linear. That's great. This is a kind of an amazing breakthrough. But if you want to prove that you have liveness, then you have to weight delta. Okay, it's part of what's happening there. In partial synchrony, you know what delta is, but you don't know when is the synchronous model coming. Yeah. So in partial synchrony, there is GST, which you don't know when, but delta, you know that the value is, you don't know when it starts, right?
Okay, because you have the other definition, which I don't know.
It's equivalent, because that unbounded number. Oh yeah. So you do a kind of exponential backoff to find it out, roughly speaking. Yeah. You do kind of exploit to figure out what is that unknown number. And yeah, so we have kind of new work. This is hot stuff, which basically, again, all these are things are small modifications and changes to the protocol, but these changes actually sometimes do a difference. And so what this does is kind of gets you the best of both worlds. So you get a linear number of messages for every view change and for leaders, and not only that, but you do not need to wait delta. So you can move as fast as the network. So if delta is, let's say, 2 minutes, then you don't need to wait 2 minutes every time you change a leader. If changing a leader takes you 3 seconds, then you can move very fast and repeatedly change leaders every 3 seconds. So this kind of turns out to be, and you can look online and find that. So I guess my point is to focus kind of on in partial synchrony, and this goes back to where's the quadratic. Let's look at the adversary in a little bit more detail and discuss kind of a static adversary versus an adaptive one, right? So a static adversary basically decides who to corrupt in advance, and then the protocol starts running. An adaptive one kind of looks at what's happening and then decides who to corrupt and when. And then there's even kind of notions of when he decides to corrupt, how long does it take until the corruption actually happens? And this is actually extremely important. So again, this goes back to this idea that in PBFT you have a stable leader, you're not replacing leaders, and keeping a leader for a long time is problematic because you can kind of attack this leader and corrupt it. Especially if you have an adaptive adversary, this can happen.
What is adaptive?
An adaptive adversary can decide who to corrupt.
But it can change, corrupt now.
Oh no, so it's not a mobile, yeah. No, not a mobile adversary, just not a mobile one. Just the one that can adaptively decide who to corrupt, but not a mobile one. For simplicity, we can also talk about mobile ones. And yeah, so this is kind of this idea that I really want to focus on later on, but it's not just about can you or can you not adaptively corrupt, but when you decide to corrupt somebody, how long does it take until you control this person? And it turns out there's actually a big difference. There's going to be a big difference in terms of upper bounds and lower bounds by these very, very small notions of whether, in the same round so you decide to corrupt somebody, and in the same round you can control this person. So you can basically delay the messages that are sent in that same round. Or if you decide to corrupt somebody, and then it takes you one more round until you can control it. So you decide to control somebody in round 3, in round 4 you control it. Okay, and that makes a big difference in terms of upper bounds and lower bounds. This is kind of the play replaceability type approach that maybe you'll see Sylvia talk about. And you can ask about 2 rounds and maybe a polylogarithmic number of rounds. So really, my point is that adaptive adversaries have a lot of nuances here. And some of the things, yes?
I just have a quick question. For practical purposes, what is the difference in terms of defending your node? This is like, why wouldn't you always take the assumption?
The strongest one.
The strongest.
Well, you wouldn't take the strongest one because maybe there are lower bounds that says for the strongest one you can get quadratic, and for the weaker one you can get linear. So that's why. That's the punchline. So the strongest one basically says that if I solve the proof of work, then maybe the minute I send one message, I can attack you. And so even Bitcoin doesn't give you that type of defense, right? It basically says, Bitcoin says if you solve the proof of work, you manage to send it to the whole network. And here it's like essentially like an eclipse attack approach, right? Where on the miner, if you send a message, if you solve the block, I can kind of learn that you've solved it and block you from propagating this information. And so kind of the big open question in this area is can you get a linear protocol that has chain quality and is adaptive against as adaptive as you can. Okay, and to me this is kind of a important question. This is related to both new results that Algorand have on the partial synchrony model, and this paper by Chan, Pass, and Shi also on partial synchrony. So I'll try to put links on, but you can Google partial synchrony and these two guys. So there's a very recent work trying to address this type of problem. I don't think it's completely solved. Okay, so this is what I want to say about partial synchrony. And so we discussed asynchrony and partial synchrony, and now we're going back, all the way back to Nakamoto consensus, which you remember Nakamoto consensus is working on in the synchronous model. So we want to, so just a few things about synchrony. So in synchrony, you can kind of build a state machine replication protocol, a distributed ledger, with the adversary controlling a minority, so less than a half. And you can actually do broadcasts with any number of failures. This is kind of the famous Dolev-Strong work. And so again, in synchrony, the question is, can you build a protocol that's linear? State machine replication. can you build a protocol that's linear, has chain quantity, and works against an adaptive adversary, or at least a mildly adaptive adversary? And the answer is, yeah, Nakamoto consensus. So you've seen that. And that's an example, at least, of one protocol that does that. So that's kind of a hint that this should be doable. And there should be other variants. And kind of, what I want to say is that this uses this idea of mildly hard cryptographic puzzles, and assuming one CPU, one vote. And there's a question, and uses a lot of energy. So the question is, can you do something similar in the synchronous world without using these types of assumptions? This is kind of one of the things that we're thinking about. And so here's one thought about this, and this is, again, a really beautiful work by Valerie King and Jared Saya and a bunch of their co-authors. And this is in 2006, and I guess plus minus two years in that area. And this is this very simple idea of electing a committee. Right? So you want to have a Byzantine fault-tolerant protocol, but instead of just running this protocol, and then I want to say this is kind of a precursor to a lot of other results they had. And the high-level idea is very simple. So we want to spend a linear number of messages, even though we have a quadratic cost protocol. So how do we do that? Well, we'll start with n nodes, and then we'll randomly choose a small committee C, let's say of Poilog size. So we'll use some method to choose it. And they have some information theoretic method. You can use cryptographic methods. And there's various ways to do that. But let's assume we can randomly choose a subcommittee. And so the idea is that if we choose a random subcommittee, then hopefully it will be representative in the following sense. If the adversary controlled, let's say, less than a half in the general population, then we hope that it will control less than a half in this committee. That's the high-level approach, at least. And then what we'll do is we have this Poilog committee, and on this Poilog committee we can run our old, expensive, quadratic, cubic protocol because it's just Poilog size, and so you get like Poilog of Poilog. That's still fine. This is nice because it works for a static adversary, and it takes some work to do it to get a little bit more adaptiveness into it. So I recommend reading these papers. And in the proof of work world, there's been similar types of results, and this is kind of Bizcoin and hybrid consensus. This is 2016 work, and again, the high-level idea is we'll use the Bitcoin chain to actually choose the committee. So let's take like the last 100 nodes in the Bitcoin chain, and they're going to be our committee. Actually, let's ignore the last 10 because remember, like you want to get some sort of commitments. You want to have some commitment, finality about who is in the committee and who is not. So let's ignore the last 10, and then you take that group and run, let's say, PBFT on this group. And here is a slide I stole from Rafael Paz. So you see this is, and Bitcoin is the same thing. Here's the Bitcoin chain. We take this is the longest path. We'll ignore, let's say, the first 10. Let's look at the remaining 90 before that. And this 90 is going to be a committee. And we do PBFT, and we become rich. So that was their plan. Yes?
What's the incentive of the last guy in the committee that is about to be voted out?
Yeah. So we have papers about incentivizing these committee behaviors. So yeah, it's that needs work. But I'm just saying this is the high. I just want to get you the high level idea. But intuitively, we all get paid, and maybe like one approach is you only get paid if you get out of the committee. So for example, but you need to do some incentives.
How do you really agree who is not in the committee? I mean, the length of the block.
Yeah, so we have papers about doing proper view change to do this, and like there's a lot of work on that. It's not easy. I mean, it's not immediate, for sure.
The amount of diversity in the committee is limited by the diversity on the chain.
Yes, and also you can see who the committee is, so it's very not adaptive, right? You can see in advance who they are. And so I'm not saying it has a lot of challenges in that sense.
How do you bootstrap it? Like you don't have the first maybe last 10.
Oh, you just do, let's say, a regular Bitcoin. You start with a regular consensus and then Nakamoto consensus. So Nakamoto consensus works, it's just less efficient. So here we, Yes.
How many people take the right to how many people can participate?
You decide. It's a parameter. So here you decide. Some, let's say 100. So
Decision for next block, you may on the block meet people who's already.
So every 10 minutes, there's a new block. This new block pushes everything. Then there's a reconfiguration, a view change event that changes the size of the committee members. But the committee members are doing PBFT, so then they can do this very quickly. So I guess one point I want to say is that this is like 2016 idea. There are, 2 years have passed, and there are more ideas. This is like just the precursor. Yes, go ahead.
So this is synchronous, right? The PBFT.
This is assuming synchrony because they're using the blockchain. Yeah.
So you said that we have very like 5 miners, basically 5 pools. With the randomness of like mining a block, how that do
Yeah.
get to not being above the threshold of controlling the committees directly?
The answer is there's no guarantee. So this is just a way, just a one way. I guess my point was just to show you the analogy between some of the more strong PODC oriented stuff and some of the much more Nakamoto concerned stuff. This is not perfect at all. It uses proof of work. It mixes it together, and this is there are many. It's just giving you kind of a nice analogy between work that has been done in the more theoretical community and work that's been done in the systems community. And there's a lot of problems with this, so don't. So this is kind of they focused on breaking this n-squared barrier. This was their goal. So they wanted to kind of do synchronous agreement, but linear. Same problem that Nakamoto was trying to do, but they were a year late. This really focuses on kind of the power of electing a committee. There's a Bitcoin hybrid consensus. Is our word Solida, which deals with a little bit with incentives and how to do the view change in a more formal way. There's Algorand, which I hope that Silvia will tell you more about. And what it tries to do is also kind of reduce the time it takes that somebody can be adaptively chosen. So you're chosen, you do something, and then you go away. This is this player replaceability approach. And then there's
Yes. Just a question about the hybrid consensus. Once you start the PFT, you still have forking, or then forking is gone?
There are several approaches, but in the Bitcoin approach, you use proof of work to decide on the reconfiguration event of the BFT. So you don't have, the forking is more about stalling the BFT from reconfiguration correctly. So the chain itself is generated by the PBFT protocol.
And there's one chain.
One chain, yeah. So so you could have forks, but forks basically mean that many people are trying to become elected as a leader. This is similar to how Paxos deals with the fact that if you have multiple leaders, then somebody will win. So the way, at least let's say in Solida, which we try to do this in a more formal way, is to basically say that if there are many people that solve together, then you deal with it just as you would deal in a partial synchrony algorithm, where one of them becomes the leader and the others don't. Right? So yeah, no forks.
How are participants identified in the case of the public consensus? Their public keys can be generated for free. How is this? This notion that participants must be weighted according to the mining power is replicated somehow when we go from Bitcoin blocks to BFT. If I'm a miner,
Yeah, good question. No. This goes back to Gun point. The people here are whoever has mining power, right? So it's proportional to it's the proportion. The same 15 people will vote themselves. So it's not. You're not really democratizing the things, right? In that sense. Again, I kind of recommend you to also look at what Algorand is doing, because it's kind of a more advanced version of these types of ideas. And really, what I want you to focus on is not this particular picture, but this idea or the power of choosing a committee. And again, this is not a new idea, right? So this is how humanity governs itself, right? We don't all make decisions collectively. We, once in a few years, vote somebody, and they make decisions for us. And there's actually some cryptocurrencies that do this. This is called delegated proof of stake. And you can imagine what happened with the delegated proof of stake, right? you vote with your stake to choose like 20 elected nodes. And so what do the elected nodes do?
Bribe you.
They bribe you. So they pay you, and this is unsurprising because in the real world, as you know, in elected democracies, this is part of what happens, right? That the parties essentially bribe their participants to get kind of benefits. Yes.
Is the chaining, is the solving the puzzle, do we assume it to be part of the definition of a blockchain? We have blockchains that is not chained by a hard problem.
So in these papers, it was explicitly said that you use proof of work in order to decide who gets to join. In Algorand and Chanpassy, you use proof of stake to decide. So there's no proof of work. You decide proof of stake to decide who joins. So again, there's a separate voting mechanism.
So it's not part.
No.
So it's not part of what Maurice talked about. If you want to change here, you have now to do a lot of work. This is specific to Bitcoin.
Yeah, well, again, the way I think about this is there's a specific thing which is who gets to vote, and then what's the protocol. So some of these are more tied, and it's harder to decouple them. But yes, you can do a lot of mixes and matches, for sure. In a way, like one of the things that Algorand did is take these ideas and use proof of stake instead of proof of work. Yeah, and so again, this is a nice thing here because what Algorand doesn't have is you get elected and then you choose what your transactions are. Remember, in Bitcoin, you first choose what your transactions are and then you try to solve the proof of work. You can't change your value, right? So if Morris has some value, I can't go and bribe him. Here, you get elected. Now I know Morris is elected. I might try to bribe him to do something. So this is kind of maybe a deficiency in the Algorand protocol, and Chanpassy has this nice approach where you're actually committed to the value. But you're committed to kind of a binary value, so they have ways to deal with that too. Okay, so really what we want to do is ask ourselves, is there a quadratic lower bound here? So do we have to kind of, if we want to do these good things, do we have to send a quadratic number of messages? Or maybe we can do this in a linear number of messages. And here I want to kind of define this strong rushing adaptive adversary. And so this is kind of the strongest version of an adversary that you would want to think about in an adaptive setting. So it can see which honest members are sending which messages to which other honest members. So it knows what's happening in the network. Not the content, but just the fact that messages are being sent. And it can corrupt somebody. And if it corrupts somebody in round 7, then it can actually block the messages that are sent by this node in round 7 from arriving to the network. So this is kind of the strongest version of an adaptive adversary.
Local corrupt.
Generate new messages and block the messages that have been sent. Okay, so it can do it basically controls this node in round 7. And so the idea here is that if I control, I can basically do an out of service on my previous messages and block them and send new messages. So this is kind of the strongest notion of an adaptive adversary that you want. And we have a lower bound that basically shows that against this strong rushing adversary, you must send a quadratic number of messages. And so this is kind of, again, extending classic lower bound of Dani Dolev and Raishuk, which does this for deterministic protocols. This is kind of an extension for randomized protocols. So even if you have randomization, this doesn't help you. And in the synchronous model, you can still do things, but you have to send a lot of messages. So for example, this is the work at Katzenku, which I mentioned, which gets the optimal resilience and the fastest number of rounds and a constant expected number of rounds, again using randomness. But the message complexity is large, so it sends like a cubic number of messages. And there's these other protocols like Definity, which again, under this strong adaptive adversary, don't have like a constant number of rounds, so it can take maybe a linear number of rounds. So one thing you can check out, we have also this new result in the synchronous model, which again gets kind of the optimal result in this sense. So you get the optimal resilience and the constant number of expected rounds, and the number of messages is optimal because there's a lower bound that says that you can't get better than that against this type of strong adversary.
Practically, the optimal resilience of n greater than 2f is really significant compared to n is greater than 3f.
I can say that the real question is how practical is the assumption of synchrony. And so that's to me the real question. So in a sense, you would always prefer to get more fault tolerance. The question is assuming synchrony practical or not? So, as a system designer,
partial synchrony is probably practical.
yeah, so I can tell you about systems. I don't want to focus too much on systems, but I guess one question is is synchrony doomed? So some people, many people from the PODC community basically say that synchrony doesn't make sense. Maybe partial synchrony is kind of a reasonable model. And so one question is synchrony doomed? Timeouts are always tricky, and maybe for liveness it's okay, it's just slow, but for safety you don't want to kind of have. You don't want your protocol to depend on. You don't want your safety to depend on synchrony. This is exactly what partial synchrony says, right? That I don't mind liveness. I don't mind losing liveness if I lose my assumptions on synchrony, but I don't want to lose safety. And I think Bitcoin is kind of an example of showing us that you can do this agreement without worrying about synchrony. It is synchronous, but you get some performance degradation in terms of the number of rounds, in terms of the time it takes. And so this property is this that I want to mention is that you actually move at the speed of the network. So again, in Bitcoin, every round takes you 10 minutes. So what you'd like to do is say, well, I have a protocol that if the system works fast, maybe I can send much more transactions. Maybe I can get a transaction every 5 seconds. But if I need to, if there's a problem, then I'll have to wait for, let's say, 10 minutes. Or maybe my safety depends on that, and so on. And so I want to highlight this new idea of Thunderella, where you can actually get a synchronous protocol, but this synchronous protocol can actually move as fast as the network, so it doesn't have to wait delta. So a lot of these synchronous protocols actually have to wait a particular parameter delta, like Bitcoin has to wait 10 minutes, and Ethereum has to wait 17 seconds or whatever. So here you kind of have a protocol which, if you assume that the adversary controls 1/2, then it still works, but you have to wait delta. But if the adversary controls less than 1/2, the adversary is kind of weaker, then you can actually move faster. And I think this is a nice type of trade-off, which shows that you can actually have synchronous protocols that, in the best case scenario, are working faster than in the other case. And and kind of the next question I think, and I think there's still more work to understand this idea of responsiveness. So how do you kind of assume synchrony but get bounds even if you get better types of results? And the next question is kind of about these different types of adversaries and getting optimal types of bounds for each one of these adversaries. So if the adversary is strongly rushing, which is kind of the worst case, then you have lower bounds. And I think understanding what are the best you can do in these other types of definitions of adaptive adversaries is an interesting open question. Okay, so I'm going to switch gears and talk about some warnings about decentralized trust, and then focus on kind of I guess some trade-offs. So I guess the first thing I want to yes.
Question. Just as a practical sense, if it takes 6 sequences to clear out a transaction, it doesn't make any practical sense to pay a visa and wait 1 hour to get the transaction to go through.
Mm-hmm.
Other coins are supposed to be faster. Do they use different technology, or what is the difference between bitcoins and other current currencies?
So fundamentally, if you are burying things with proof of work, then waiting an hour equals waiting an hour. It doesn't matter on which scheme, right? So you can't do something that waits less than an hour if you want to get the same type of guarantee. If you have a scheme that gives you, let's say, a block every 10 seconds, then you can get more granularity. So instead of having like 6 places to stop every hour, you can have many more places to stop every hour. But fundamentally, what you want to do is want to bury your transaction with enough time. So it's really about time. It doesn't matter how many blocks or how big the blocks are and so on. Because the time basically is a function of how much compute power is being buries this transaction. Right? So this is what you want to do. You want to bury this transaction by a lot of compute power. And so the only way you can measure compute power is by giving it time. So it doesn't matter what compute power I'm doing, what magical hash function I have. What you're doing is saying I want to do that magical hash function for 3 minutes or 1 hour. So it might be that for a pizza I'm willing to wait 3 minutes, and for my house I'm willing to wait 1 hour. And then, if I have a scheme that only gives me 10 minutes, I'm losing that granularity. And hopefully I will talk tomorrow also about some of these payment channels and so on. So there are ways to get like much faster finality.
So you're saying that the only security is a matter of time, right? This is true, I think, for the case where we do assume no attacker has like more than 50%, but if you do speaking about blockchains with more granularity and blocks every 2 seconds, then if we're assuming an attacker with less than 50%, then we do get a similar security after a lower time.
I don't think so, no. I think if you do the math, you will get the same. Basically, again, you have to do the math, but at the end of the day, you want to say what is the probability that if I've worked for an hour and I control, let's say, 2/3, somebody that has 1/3 would manage to outpace me.
Right, so you get the exponential decay much faster. No?
Vitalik had crunching numbers. There's a nice blog post wrote
I think I have.
He shows that he compares the probability of reorg Bitcoin and Ethereum. He shows that after like 16 or 17 blocks, which come every 17 seconds, is equivalent to the 6 block rule.
Okay, so I'll be happy to look at it. So maybe I'm wrong. I'm definitely not kind of an expert. My knowledge is essentially that there are no magics here. At the end of the day, it's about how long you wait.
Yeah, if you assume an attack with more 50%, but
Yeah.
if you are discussing an attack with less than 50%, then you have an exponential decay within the number of blocks.
Aviv.
Yeah, so I think the way to resolve the mystery is that if you could take Bitcoin's limit down from 10 minutes to, 10 seconds, the thing that starts to ruin the day for you is the delay, right?
Okay.
So you could get more granularity, but that only meant to have lower delay than that to begin with to be able to do the same.
I see. Okay.
So you do get the exponential speed up, but only if you don't have the same speed.
Okay.
So not really. Of course, there's no free lunch here.
The
Okay,
point is the
okay.
question of the variance. So a block every 10 minutes has the variance is very high, but if you have very small intervals, then the variance is small and closer to the expectancy. So it
Yeah.
should be faster.
Yeah. So
It's correct to measure the proof of work better if you do it very, very often, but
Yeah.
you don't hear about messages from others.
yes. Okay. Yes. Yeah. So thank you. So I guess ideally, we'd like to have a scheme that. So if you in an ideal world, you would like to say that it just matters how much you wait, but then you'd like to have, let's say, every second a block, just so that you can wait. You can decide how many seconds. The problem is that, as Aviv points out, that now you start getting the problem of too much contention. You don't have one chain. You have more than a chain, and then you got here the world experts of how to solve that problem. Which I'm not going to discuss today. I do want to discuss, and actually this is a good point because you will hear a lot of people saying I read a blog post about one person and the other, and there's millions of dollars, billions of dollars, and so on. And so I want to say there is kind of a fundamental trade-off between performance and decentralization. So this is kind of the first fundamental trade-off. So on the one hand, we want to get decentralization. On the other hand, decentralization means that you're going to pay with performance. So basically, it means that if anybody gives you any extreme version, it says I can do 50,000 transactions per second or something like that, then this is probably why? Because in this dimension between decentralization and performance, this person chose performance, right? So like Oracle databases can do 50,000 transactions per second, but they don't give you decentralization. So I guess my point is that if you have something that has extreme decentralization, it's really good, but the performance is bad, then you just say, okay, this is probably a bad system. But the other way around is typically harder because people have like these extreme claims and saying, oh, system A is like the best in the world, it does whatever, and so on. And it's hard to actually pinpoint and figure out, yeah, but maybe it's just built on 16 machines or 15 miners or 5 groups, and so on. And so one of the things that I would recommend to you to do as people who are kind of coming in academia is ask yourself, does this scheme at least solve some variant of Byzantine fault tolerance? So it might be some probabilistic variant, it might have some weaker liveness or weaker safety, but does it actually solve some Byzantine fault tolerant problem? And then the next question you should ask, because some of these people, let's say, implemented Raft or Paxos or Kafka or some other thing. And the other question, so once you realize that this actually protects against Byzantine faults, then the next question is, okay, so how many? So how much decentralization do you have here? Is it a system that the way it's deployed is actually protecting against 5 failures, or 3, or 5,000? So ask yourself, how many failures can you stand? And specifically, if you look at systems paper that are being published in this area, then you ask yourself, how are these evaluations done? Is this just really spread over the whole world and really built, or were there like 3 or 4 virtual machines on some single server? Going back to looking at systems papers and evaluating whether they actually provide decentralization or just performance, are they actually, these transactions actually being written on disk? So you actually have one system that writes it on disk. Some people just reporting, extreme performance, but because they're just doing nothing or doing something in memory. And again, that doesn't really give you anything. And again, you can ask, are you just doing payments? Or are you doing something more complicated than that? Okay, and so this is kind of one trade-off that I want to focus on, and I want to focus on do you want to have time for questions, or what do you prefer?
Question?
Yes. Should I leave time for questions, or? Okay, you ask. Okay, so I'll just go online. Yeah. So.
It is an adaptive question.
Yes.
What difference should be in the blockchain, whether ironically just money transactions or smart contracts?
It's just that when you tell me about your performance, I want you to be very clear about what you've measured. That's all. And I think if you are running complicated code versus if you're measuring a put-get in a key value store, then obviously there's going to be a difference in performance. And so I guess here...
It's just a better performance. In the blockchain itself, it's just...
there's an execution engine, and I think one of the things that people fail to do is precisely define what their execution engine is doing, let's say, in their benchmark.
Another one is signature validation.
Yeah.
A lot of
Oh, so this goes here. Is it really fault tolerant? Like if it... Oh, the client side.
Oh, yeah.
The client side. Yeah. I've seen crazy. Yes, of course. Yes, the client side. That's a good point. But yeah, I guess is it really Byzantine fault tolerance? Does it solve validated Byzantine agreement? So solving validated Byzantine agreement actually means that the messages are signed and you actually verify them. So that your comment would actually be broken just by saying it doesn't even solve Byzantine agreement. So I'm saying they're signed, right? The client signs them.
Yeah, the transactions, not agreement on the block.
Yes. So in the definition of validated Byzantine agreement, the transactions are signed by the client. So if you're solving validated Byzantine agreement, but you're 100% right.
He's talking about something different. I think in some experiments, it will not even validate transactions. They will run empty messages and just.
Yeah. Well, okay. So as there's some systems people here, we all know there are many ways to be untransparent, and I guess my call here is be transparent and be very clear about what you're doing, because that will improve our community as an academic community that is clear how and what you benchmarked. Because then when you make a claim like 50,000 transactions per second, it's clear that you've done it because maybe you just see transactions and just throw them into your DevNull, and it works really well. Okay. I want to talk 1 minute about 2 things, which is privacy and incentives. And I'll talk about the second trade-off in the decentralized star. So the first one was performance and yes.
A quick question on the performance versus decentralization. What's your opinion on the view that we can have best of both worlds by going layer 2? So, for example, like Lightning Network.
I will talk about layer 2 tomorrow. So it's layers are great, and I was focusing just on
having the both through economic incentives, basically, this game theoretic kind of.
Layers can help. Hierarchies are great. Sharding and scaling is wonderful. I will talk about it tomorrow. Yeah, so again, second fundamental trade-off is performance versus privacy. So all I've talked about now is just about performance, but providing you with no privacy. And again, very similarly, there are a lot of papers, especially from kind of the crypto world, that give you extreme strong versions of privacy. But you look at the performance and it's bad, and then it's easy to detect and say, okay, that's probably not practical. The other way around is harder to detect. I guess there's kind of these versions that give you extreme performance, that give you privacy, but don't provide you with a real trust decentralization. So make sure that if somebody's providing you privacy, it provides you both privacy and trust decentralization together, because getting them together is kind of harder.
What's an example of that? Like ring signatures, like Monero, is what you have in mind?
No. So for example, if you have this validation approach where you have a group of validators that run a private transaction inside your permissioned blockchain. So yeah, you can kind of shard your, so in a permissioned blockchain, what you can do is you can shard your system into groups and say, each group is going to be private. It's private, but then nobody sees anything connecting between them. Yeah, so I think potentially like Zcash and Monero, Zcash is kind of in the maybe bad performance, and maybe Monero, has maybe sometimes weaker types of privacy guarantees for some things, but getting better. Oh yeah, I can say a lot about it, but I don't. Yeah, what do I mean by privacy? What I mean by privacy is that if you have a business transaction, then you get to do the transaction without people learning more than what you need for this business transaction. So that's a very utility-based definition. So that's kind of that's the business aspect of it. So with auditing and with regulation and so on. From a formal specification, this is a kind of ideal real-world implementation. You have an ideal functionality. It defines some sort of reasonable notion of privacy. There's an anonymity set and so on, and you can define that. So I could give 2 hours on that too. So there's a lot of work there, right? Actually, Aviv is going to talk about some of this stuff, amazing stuff. There's a whole week, right? Anyway, so you have to kind of figure out, what the privacy is. I'm running over time. So this is kind of, so I guess there's a lot of things about performance. I'd like to say one more thing which I think is important is kind of this, I didn't touch at all about it today, or a little bit, is this, good guy, bad guy versus rationality. At the end of the day, a lot of the excitement here is about the fact that it's a cryptocurrency, that people are making money, and that they're actually motivated not by, bad guys and good guys trying to defend against the bad guys, but about people who are trying to make payments and make money and so on. And so kind of, in the traditional distributed computing world, you have honest players and you have an adversary, and the goal is kind of to have the adversary not be able to do anything. So in a sense, like the good guys are running some protocol, and you want the protocol to be safe or to be fault tolerant and so on. And really, in these real-world scenarios, there's often much more of a game theoretic notion here. And so participants are not good or bad. They actually just want to, they're rational. They want to have a nice life, buy a Lamborghini, I don't know. And what you really want to do is you want to kind of get notions of game theory and coalition resistance. And one of the important things here is that people then stop behaving completely Byzantine, but they're actually driven by some fear. So for example, part of the reason why, let's say, we report our taxes, or we don't, or when we go to a bus, we actually pay for the ticket in the bus, is because we're afraid of getting caught and being punished. So the way that society works today is really about using kind of the power of punishment. And this gives you a lot of nice things. And again, this is kind of combining these both notions together. So I want to very quickly recap some of the open questions that I mentioned. I think the most important ones are the macroeconomic ones. How do you avoid monopolies? How do you prevent briberies? And how do you kind of reduce this rich get richer effect? I think this is, to me, the biggest major questions in these types of protocols. And then you in particular, like how can you avoid this $1, one vote world. And then you have kind of more, BFT type questions related to Byzantine fault tolerance. All right, thank you.